Hi, this is Matt McCormick, the Department of Philosophy in California State University, Sacramento. My email address is mccormick@csus.edu, and there's my website address. This is the lecture for my critical thinking course about understanding statistical arguments. All right, so as a review from last time, recall that we had a discussion about scientific reasoning versus anecdotal reasoning. And an anecdotal evidence, when we use it just to justify the things we believe, is stories from friends, single cases we can remember, intuitive guesses, recollections from our own experience. And those are usually not good grounds for drawing conclusions about trends, rates, problems, or large-scale phenomena. And I call this reasoning by anecdote. So the problem is that, oftentimes people will make some sweeping generalization about the school system, about some social problem, about politics, about any number of things on the basis of some tiny singular case that they've had experience with. They'll decide that Hondas are better cars on the basis of one Honda they had or one story they've heard. They will conclude that an herbal remedy or a cold remedy like Airborne works because they remember trying it one time and feeling better. So those are anecdotes, and those don't work well to give us reliable, justified conclusions. They turn out to be true on occasion. Sometimes we accidentally get it right this way, but as a means for justification, they're not nearly as reliable as the scientific approach. And the scientific approach requires that we do some statistical reasoning. That is, we gather information about large groups and we identify populations and identify properties in populations, and then attach some sort of more accurate rate number to that larger scale. So we often need to know the percentages of a property in a population. So here's an anecdotal argument. For example, nuclear power is too dangerous. Somebody says, my uncle died in an accident at Wolf Creek, and people die every year in accidents at nuclear power plants. And that on the surface sounds like it's some pretty good reasons for thinking or being suspicious about nuclear power, but then look at the statistics here and look at how important having the statistical information at our disposal really makes a difference here. So in 2010, there were 3 nuclear power plant workers who died out of 120,000, but in coal miners, that works out to be about 0.0025% of nuclear power plant workers, whereas with coal miners, which is our other major source of electrical power, 48 out of 82,000 coal miner workers in 2010 died, or 58 per 100,000, or 0.004%. Now, I've got a lot of numbers there, and it can be hard to sort of sort through those, but the real important point to see there is at the end. So what percentage of nuclear power plant workers die? 0.0025. What percentage of coal mine workers die? 0.004. And what that means is that coal mining is actually twice as dangerous as nuclear power plant work. So your anecdote about someone's dying at Wolf Creek might be true, but it doesn't give us the real rate. What we need to know about which is more dangerous, for instance, is some statistical information. And statistical information reveals sometimes something that's quite contrary to common sense and something that's quite contrary to the anecdote that we might have personal exposure to. That's because as you find your path through life and through different experiences, your sampling or your encounters with these phenomena, with nuclear power plant workers, or with any number of other, or with cold remedies, or any other number of phenomena, your personal encounters with them are not necessarily representative of what's happening at the large scale, at the scale of thousands or millions or 300 million Americans. So if you ask an emergency room nurse, how bad is the drug problem? Well, she or he is going to have some really horrific stories about how awful drug use is. But of course, what the emergency room nurse never sees is all the people who try recreational drugs and don't end up in the emergency room. So the emergency room nurse doesn't know about the good cases, about the successful cases, about the non-harmful cases. She or he just knows about the harmful cases. So she's going to have a skewed picture. And this is not to say one way or another about drug use necessarily. It's just to point out that your personal anecdotal experience of some phenomena is not representative of what might be going on at the large scale. Okay, so your intuitions, your personal history, your stories aren't reliable indicators of trends, facts, or large phenomena. So somebody might say, San Francisco is way more dangerous than Sacramento. My cousin got assaulted while he was walking down the street. And there's the kind of story or kind of evidence somebody might give for that claim. And there's a kind of intuitive pull to this. It sure seems like San Francisco would be more dangerous than Sacramento. Well, it turns out when you look at the statistics here that the assault rate in San Francisco is 2.6 per 1,000 people, and the assault rate in Sacramento is 4.5 per 1,000 people. That is to say, assault is twice as likely in Sacramento as in San Francisco. So you're better off going to San Francisco if this is what you're worried about. So in statistical arguments, there's a number of concepts or properties or ideas that we've got to get across. Actually, there's 7 that we're going to talk about today, and the first 4 are these. We need to identify the measured property, the target property, the sample population, and the target population. So in a claim like, here's some examples of some statistical conclusions. 18% of Americans smoke, 40% of people in France are overweight, 35% of Americans are overweight, and 1.4% of children have autism. Now, all of these numbers are really important because, like, take the autism example. Lots of people out there forming opinions about what's causing autism, whether or not autism is going up or going down. Lots of people out there who have opinions about who's overweight, whether or not Americans are more overweight than the French. Turns out that the French are actually more overweight than Americans, contrary to public opinion or common sense. 18% of Americans smoke. Well, we want to know that because we want to know whether the trend is going up or going down and what's happening next. Okay, so those are statistical sentences. And just as a preview of what's coming next, the format of a statistical sentence is X% of a property is present in a population. And so 18% of Americans smoke. In that sentence, we actually have, or actually, I'm going to use the second one because it's a better example. 40% of people in France are overweight. So the property in the second example is being overweight, and the population is people in France. And that's the standard layout for one of these sentences. Now, in these particular examples, we're actually talking about the target property and the target population. And one of the things I have to do in the next few slides is explain the differences between those and the measured property and the sample population. And less than 1% of bats have rabies. And let me just point out that the target populations in all of these sentences are Americans, people in France, Americans again, children, and bats. And the target properties are smoke, are overweight, oops, yep, that's right, have autism, and have rabies. So in these 5 examples of statistical conclusions, those are the target populations and those are the target properties, just to get you start practicing identifying what's what in these kinds of arguments. Now, I'll explain what the rest means shortly. Okay, so since we often cannot examine all of the members of a target population, we select a sample population. So, for instance, 18% of Americans smoke. Well, there's over 300 million Americans, and we just can't go and poll every one of them. We can't talk to every one of them. We can't watch every one of them. We can't know directly by observation what percentage of them smoke. We actually need a sample population. So we just need a smaller group that we can look at, and we use that group to project or to broadcast the conclusion up to the larger group. So the sample population, the definition of a sample population is the set of individuals, usually a subset of the target population, that are actually studied and extrapolated from. So the idea in a statistical argument is usually that we are going to take, we're interested in some larger group of things, like Americans or trees or bats or whatever. And since we can't examine, or it's not practical to examine all of the things in the target population, we're going to look at a smaller group of them. So we'll look at a sample population and we'll use them to stand for the target population. Now, why is it important, or what do we have to worry about when we're doing this? Well, one of the big issues we have to worry about when we're moving from sample population to target population is something called representativeness. The sample population must represent or resemble the target population in ways that are relevant to the property being measured. And here's what I mean. A small Amish community in rural Pennsylvania is not representative of Americans on the whole. So if I was wanting to find out about drug use or about cell phone use or any number of other interesting properties about Americans, I could look at that Amish community, but the results I would get would not stand for or represent or look like what Americans look like, because the composition of that sample population is so skewed compared to the composition of Americans at large. Amish, of course, represent a small part of the American population, but we don't want them standing for all 300 million, because their behaviors, their activities, their habits, their things that are true of them are not true representatively of the rest of the United States. They're just true of a tiny portion of them. So what we typically need in our sample population is a large randomized sample of people, if we're talking about people instead of bats or trees or something else, from different areas of the country with different ethnic, cultural, economic profiles that match the whole country. So for instance, if you wanted to know how much time are Americans spending on Facebook, well, you'd certainly want to get a large randomized sample of people from different areas of the country with different ethnic, cultural, and economic profiles that match the whole country, and you look at that as your sample population. You find out what their Facebook use is in that group, and then you use that to project onto 300 million Americans. But you wouldn't just look at that small Amish community in rural Pennsylvania, or you get a really skewed result. Okay, so another way to talk about this is to say that there's a target property in the target population that we're interested in. So in some of these examples we're talking about, the target population is 300 million Americans, for example. And typically we can't look at all 300 million Americans. So what we'll do is we will extract out a sample population. Now, the way the Gallup organization does this, and they're a very good, very reliable, a very good organization. They really know what they're doing on this. They will go find as many as, say, 3,500 people selected for a Gallup poll. And you may have participated in one of these polls. They'll call you, or they'll give you a questionnaire and ask you to fill out a bunch of questions to find out what you think about something. So what we do then is we take that sample population, say 3,500 people selected for a Gallup poll, and we're going to use them to stand for 300 million Americans. And we examine a measured property in the sample to determine the presence of that property in the target, that presence of that in their target property. So let me give an example. Here's an example of a Gallup poll that was conducted recently. They took a bunch of people and they asked them this question: do you agree that life on Earth evolved, in the survey? And they gave them a bunch of options. They could say yes, they could say no, they could say don't know. And in this case, what's the thing we're measuring? Well, we're measuring them checking off a bubble or checking off a box in our survey to a question. Now, why is that important? Well, it might be important because of this. What we really were interested in this particular statistical survey was, do Americans believe that life on Earth evolved? And there's a difference between whether or not someone answers the question yes, do you agree that life evolved, in a survey, and whether or not someone actually believes that life on Earth evolved. Now, what's the difference? Well, think of the cases where somebody might answer yes, but they actually don't believe it. So there might be somebody who misunderstands the question and answers yes, but in fact they don't believe it. And there's also cases where somebody might actually believe that life on Earth evolved, but they answer no because they feel self-conscious, because they're worried about the backlash from their family. Maybe they're worried about what their priest would say. Any number of other and reasons we maybe can't anticipate, or maybe they're confused. They give an answer that doesn't represent their real belief. So typically when we're measuring something, there's some possibility of error. There's an error rate associated with the thing that we're measuring. And asking somebody a question about whether or not they believe something or whether or not they agree with something may or may not actually capture or accurately identify the thing that the property that they possess. And really what we're talking about here is accuracy, and that's going to be the big issue that's going to come up next. Okay, so think about that when you're taking your next poll, and let me give you some more examples. So in many cases, our measurements are different from the target property. The measured property turns out to be different than the target property. And I'll give you an example, and this should bring it out. Consider how many people have reported a bike theft to the police versus how many people have had a bike stolen. Those rates are very different, right? Because lots of times you'll have a bike stolen. I've had a couple bikes stolen in the last couple of years, and I didn't report either one of them. So the number of people who have had a bike stolen is actually higher than the number of people who reported a bike theft to the police. Or here's another really obvious one, reported a rape or a sexual assault, compared to whether or not the property was raped or sexually assaulted. There's lots more people who have been victim to rape or sexual assault than who have reported it. So if we're measuring how many people report, we're going to get a very different number, a lower number than actually occurs in the population. Now, this is not to say that we can't compensate for the gap or the difference between measured and target properties. But in statistical arguments, we need to be aware of the difference, and we need to think about how is the measured property, what is the measured property, and how is it different from the target property? Because they're very often different, and importantly different. You may have thought about this one, tested positive on a home pregnancy test, which sometimes comes out wrong, versus is pregnant. There's a difference here because home pregnancy tests have false positive rates with them. They have false negative rates with them. Sometimes you test positive and you're not pregnant. Sometimes you test negative and you are pregnant. So whether or not you're actually pregnant is a different property from whether you measured testing positive on a home pregnancy test. And that's why you take another test or you go to the doctor and get some other way to check it. Consider the people who have checked the box that says agree to the question, do you believe that life on Earth evolved, versus believes that life on Earth evolved. So notice that all my target properties here are verb clauses. They're descriptions of properties that people have. A person's pregnant, a person suffered from sexual assault, a person had a bike stolen. So the people in these cases are the populations, and the properties they have are these two examples, these two columns. We measure one and we use that to stand for the second. Or somebody might test positive on a blood test for Bacillus pestis, or Yersinia pestis, and what that means is, if you ask a virologist, is that that person has bubonic plague. And those tests can be different. Or the really timely one in the news right now is testing positive for Ebola versus has Ebola. Some of our testing mechanism for Ebola is not very accurate. And you may have been through this if you've been in the hospital for some other kind of disease and had a battery of tests done. If there's an error rate associated with the test, then there's a gap between the measured property and the target property. And we have to be aware of those when we're developing strong statistical arguments. And that's the idea here, is that these are inductive arguments, and when somebody's doing good science, what they want to do is develop a strong argument for this move. They want to be able to argue from the sample population has a particular measured property to the target population has a particular target property. We're going to make that inference in statistical arguments. And the big issue we've just been talking about is accuracy. In order for one of these arguments to be strong, to be compelling, the measured property should be an accurate indicator of the target property. So I've asked this question in class, raise your hand if you've ever had a sexually transmitted disease. Of course, nobody raises their hand to that. There's other better ways to fill that out. If you were to fill out this anonymous questionnaire accurately and receive $50 for filling it out, we can get people's response rates to come up to, say, 21% or something like that. So the measured property turns out to be very different depending on how you measure. The way you measure something in a statistical argument makes a difference. Okay, now the next concept we've got to deal with here is called margin of error. And this is something that researchers, what it means is the margin of error is the extent to which researchers believe the presence of the target property in the target population may vary from the presence of the measured property in the sample population. So the amount of slip or the amount of gap between those two things. So the margin of error in that have you ever had a sexually transmitted disease survey that I just conducted where I asked everybody to raise their hand. The margin of error in that example is very, very high. But when you look at a good Gallup poll, and they they conduct their survey, their questionnaire the right way, they do it anonymously, they do it very carefully, and they've done lots of statistical analyses on these types of polls, they can determine that, look, we want to know about 300 million Americans, and what we did is we looked at 3,500 Americans, and we measured them in this way and this way, and we figure that the results we get are plus or minus 3% accurate. That is, the margin of error is plus or minus 3%. So suppose they decide that 18% of Americans smoke, and then they attach a margin of error to that of 3%. So what that means is, in our sample population, we figured out that 18% of them smoke. And we figured that the margin of error is plus or minus 3%. So in the target population of Americans in general, we figure that the rate of smoking could be as low as 15% or as high as 21%. But we're in the neighborhood, we're close. We're pretty close to the target. Okay, so a sample population is the group of objects that the study actually measures. We've seen that. The target population is the larger or largest group of objects that the study seeks to draw a conclusion about. We've been looking at cases where you're looking at Americans, for instance. It might be humans, it might be ground squirrels, it might be trees, it could be any number of things. The measured property is the property or feature in the sample population that is actually measured in the study in question. And the target property is the property or feature in the target population that is central to the overall argument. Okay, so here's an example, a real case. In a broad survey of the medical records of more than 10,000 cancer patients across the country, researchers at Johns Hopkins have concluded that 82% of stage 0 lung cancer patients whose cancer is detected early survive. Okay, so the property here is survive. That's to say, over the course of several years, the records of 10,452 patients were carefully reviewed to determine at what stage the cancer was detected, how it was treated, and what the survival rates were. Early detection was defined as cancer that was confined to a small area of one lung. Survival was defined to mean surviving 5 or more years after diagnosis. Okay, so here's what we're wondering about. In the population of Americans at large, there's a percentage, or there's a number of people who have cancer. Suppose it's lung cancer in this case. And we're interested to know, okay, now if we identify somebody with lung cancer early on at stage 0, what are the odds that the treatments we give them will lead to their survival? Now, we can't look at all the cancer patients. We don't know who else got lung cancer in the whole country. We can't afford to, or don't have the time to look at all of them. But we can look at these 10,000 people. And what we did is we tracked those people, and we decided, okay, when it happens this way, when these people had lung cancer, we treated them this way and this way and this way, 82% of them made it. So this is going to be good news, right? This is, if you've got a relative, an uncle or an aunt or somebody who goes in the hospital and they get diagnosed with lung cancer and the doctor says, you're at stage 0. And the very first question everybody in the family has is, okay, what are the survival rates for people who've got this? And the doctor can pull up this survey, this study, this statistical analysis and say, well, typically what we've learned in the past is when we looked at these 10,000 patients, 82% of them made it when we treated them this way. So that means that, plus or minus, with some margin of error, there's good cause for optimism here. Your uncle, who's got 0-stage lung cancer, has got an 82% chance of survival, or it looks like somewhere in that neighborhood, which is much better than, say, a much more dim prognosis. Okay, so in this case, the conclusion is, in general, 82% of people with stage 0 lung cancer survive. What's the sample population? It's the 10,452 patients in the Johns Hopkins study. What's the measured property? They had medical files that indicated survival from lung cancer 5 or more years. Now that's different than actual survival, right? Because what happened in the Johns Hopkins study is they went and got the medical records and looked at them. Now somebody might have filed the records wrong. They might have made some records of somebody as dying who didn't die. They might have made a record of somebody as having lung cancer who didn't have lung cancer or had some other kind of cancer. There could have been any number of mistakes made. But this is what the Johns Hopkins researchers did, is they looked at those files. And who are they interested in? They're interested in, generally, with people with lung cancer that's detected earlier, 0-stage lung cancer. And what is the target property? What are they interested in? They want to know how many of those people, what percentage of those people survived 5 or more years. So we've got a sample population and a target population. And what we found out in the sample population is that 82% of the 10,452 patients in the Johns Hopkins study reported surviving lung cancer. And on the basis of that sample population and what happened with them, we project up and we make this larger conclusion. We say, okay, it looks like 82% of lung cancer victims survive, as long as it has sort of roughly these parameters. And that's a really useful number, and that's really helpful, right? And notice how much better founded, how much better justified this sort of reasoning is than, say, an anecdote. Your uncle gets diagnosed with lung cancer, and then somebody else in your family goes, oh, I knew a guy who had that, and he died. Well, that anecdote tells you that nobody survives, if that's all we're going to take as our evidence. Or that person says, I know somebody who had that and they got better. Well, it turns out they happen to be right. Typically, people do get better, but now we've got some really accurate, clear, well-justified numbers. We can say, look, 82% of people make it if they have this kind. So it's an incredibly valuable, incredibly powerful, useful thing to be able to generate an accurate, reliable, representative, strong argument for a statistical conclusion. Vastly better than the anecdotes that we typically use. Okay, so here's another number. A few years ago, the rate of smoking was much higher. Here's the conclusion. 21% of Americans smoke, and here's the study. In a recent Gallup poll, it was concluded that 21% of Americans smoke. Interviews with more than 75,000 individuals across the United States indicated that about 16,000 of them smoke at least one cigarette or cigar a day. Gallup interviewed no fewer than 1,000 U.S. adults nationwide each day during 2008. These results are based on 75,073 surveys conducted from 2008 to March 17th, 2008. For results based on this sample, the maximum margin of sampling error is plus or minus 1 percentage point. In addition to sampling error, question wording and practical difficulties in conducting surveys can introduce error or bias into the findings of public opinion polls. But this is another very useful and very valuable study. Consider that we've had this massive marketing campaign, this anti-smoking public service announcements that have been out there for years and years now. We've been deluged with all of these ads, all of these public service announcements, with all of these people coming up with really creative ways to encourage you not to smoke. Now, this survey in 2008 shows the rate at 21%. Recent surveys show the rate as low as 18%. So it really looks like something's happening. It looks like the rate of smoking is going down in the United States. And that's why one of these studies is so important. So in this particular case, let's identify all of the major players. So the conclusion is that 21% of Americans smoke, but we only looked at 75,000 individuals across the U.S. in a Gallup poll. The measured property is they reported smoking at least one cigarette a day in the Gallup poll. And you can sort of imagine what kind of problems there might be with reported smoking at least one cigarette versus actually smokes at least one cigarette a day. People's memory is bad, they have optimism bias, they tend to understate things that are bad and overstate things that are good and make all sorts of mistakes. But I'm offering objections here, and really we just wanted to identify how do you make a strong statistical argument. The target population more generally is Americans. We know that from looking up here at the top line that says Americans smoke. And the target property is smoke. That is, we want to know how many people report smoking, and we're going to infer how many people smoke on the basis of that. So in this case, we end up finding out that 21% of the 75,000 people in the sample population report smoking at least one cigarette a day. And on that basis, we draw the conclusion, more or less, plus or minus 1%, 21% of Americans smoke. Okay, so you can see how these arguments work. What they do is they start with initial premises that are about a sample population and a measured property in that sample population. And then they need to argue for accuracy and representativeness. And those are two very different things. They need to argue that the composition of our sample population is representative of our target population. And they also need to argue that the thing we measured in the sample population, the measured property, is an accurate indicator of the target property in the target population. Okay, so 8 concepts. Sample population is the group of objects that the study actually measures. The target population is the larger or largest group of objects that the study seeks to draw a conclusion about. The measured property is the property or feature in the sample population that is actually measured in the study in question. The target property is the property or feature in the target population that is central to the overall argument. Accuracy is this notion that the measured property must accurately indicate the target property. Representativeness is about the populations. The sample population must represent or resemble the target population with regard to other properties that are connected to the property in question. The margin of error is the extent to which the target property in the target population varies from the presence of the measured property in the sample population. And one more idea that I haven't talked about yet is random sampling. And here's the idea. If a sample population is randomly sampled from the target population, what that means is every member of the target population had an equal chance of being chosen for the sample. Now here's the idea. We want sample populations to represent target populations. We want them, remember the point about the Amish in Pennsylvania. So we want our sample population to resemble or to represent, say, Americans. Now, one of the ways to make sure that the smaller group, say like in a Gallup poll of 3,500, one of the ways to make sure that those 3,500 people represent or look like Americans more generally is that we randomly select people from Americans at large and then we put them into the sample population. And randomness here will make sure that if, say, 10% of the American population at large is, or 11% is African American, and if 51% of the population at large is female, and so on and so forth. If we randomly select members out of the larger population, we've got a good chance of getting roughly the same proportions or same constituencies or same groups into the sample population. We get that sample population to look more or less like the target population. And that's good. Random sampling is one way. Now there's other ways to do it, but random sampling is one way to achieve representativeness when we're trying to figure out how to extract a sample population from a target population. And the way to do that is to use a method that makes every member of the target population have an equal chance of getting chosen. So if I only pick out people from urban areas, for instance, if I only talk to people from Los Angeles and select them from there in my sample population, well, there's no chance for me to get people from Des Moines or people from New York or people from rural Texas. So that method is not a random sampling method if it doesn't give an equal chance to somebody from Texas getting chosen from somebody from Los Angeles getting chosen. Okay, so there's our 8 major concepts for statistical arguments and the major ideas and principles and the major structures that have to be done in order to make one of these arguments strong. The next thing we'll be discussing in our course is how correlation arguments work. So get all of these concepts mastered before you take this quiz, and correlations is going to build on the notion of statistical arguments.